I animated the dehydration synthesis of maltose in 3D. Here's how. The animation was created in Blender, a free 3D modeling software. I wrote out my approach step by step on the Cuvette Collective website so that anyone could recreate what I did, but for any chemical reaction. If you just search for animation, it'll take you right to the post. First, we're going to start with just downloading the software, and then we'll get into how to use it to create your animation. Let's just start by downloading PyMOL. PyMOL is a popular molecular visualization software that's free for educators and used for modeling and visualizing 3D structures of biomolecules. This can include proteins, DNA, RNA, and small molecules. So you just fill out your information, and if you are a college student or an educator, they'll send you the download URL along with your license credentials so that you can use the software for free. Next, we're going to download Blender. Blender is a free, open source, and highly capable 3D modeling and animation software. It has a steep learning curve, but offers a wide range of tools and features. Last but not least, let's download Atomic Blender. Atomic Blender is a Blender add-on that bridges the gap between molecular visualization software, like PyMOL, and Blender. We're ready to start animating. I'm Dr. Rosa. I'm a chemist who's dedicating their career to helping scientists translate their technical research into broader societal impacts. Thanks for being here. Let's get to animating. We're going to break this down into 5 steps. Step 1 is preparing your reactants using PyMOL. Step 2 is importing your reactants from PyMOL into Blender. Step 3 is animating the reaction in Blender. Step 4 is setting up the world background for what's surrounding the reaction. And step 5 is rendering the animation. First, we're going to confirm the configuration of the reactants, and then we're going to search for their 3-letter code. This code will allow us to fetch the correct reactant and put it into PyMOL. When creating molecular animations, it's crucial to use the correct configuration given the context of your reaction. In this example, I'm animating 2 monomers of glucose in aqueous solution undergoing dehydration to form maltose. As a result, the open chain configuration of glucose is inaccurate for this context because in aqueous solution, glucose is in its pyranose form. Furthermore, the beta-D-glucopyranose form is more stable in a polar solvent than the alpha-D-pyranose form due to the diminishing of the anomeric effect. This is why it's so crucial to research the most relevant and abundant form of whatever you're animating in the environment or context you intend to animate. So now that we've confirmed the configuration of our reactants, we're able to search for its PDB code to import it into PyMOL. So you're going to navigate to rcsb.org and find the search bar. Here you'll enter relevant keywords related to your reactants of interest. This could be a protein name, an organism, a ligand, etc. Since I've confirmed the configuration of my reactants, I'm going to type in beta-D-glucopyranose. Next, I'm going to click the drop-down on Tabular Report and select Ligand or Ligand. From the search results, click on a structure to view its summary page. Here is beta-D-glucopyranose. I can confirm that it's the correct configuration using the ligand image. And here is our 3-letter PDB code or the ligand ID. This 3-letter PDB code is what lets us fetch the molecule in PyMOL. All right, so we're gonna open PyMOL and load the molecule to the interface by using the fetch command. We're gonna type in fetch and then our 3-letter code. And here we have our beta-D-glucopyranose form. To export the structure in a format that Blender can read, we're gonna do File, go down to Export Structure, Export Molecule, and then go over to your PDB options, uncheck Right Segment Identifier segicolumn, and click Save. Here you can type in a name, and just make sure that you change the format to PDB. Once you locate your file, you're going to open it with a text editor. Next, we're going to delete all the rows with Connect. This gets rid of small disks that PyMOL uses to represent bonds between atoms that just become kind of a headache to animate with. But if anyone has an alternative suggestion, let me know. All right, once you save your file, we're ready for step 2. If all of this animation is too technical and time-consuming for you, consider hiring our firm Cuvette Collective to do the service for you. Step 2 is importing our reactants into Blender. We're gonna open Blender and start a new project. Blender projects start with this cube in the center here as a hello world situation, giving you your first object to manipulate. You can delete this cube by going to the scene collection panel up here, right-click cube, and select delete hierarchy. Next, we're gonna ensure Atomic Blender is enabled by navigating to Edit, Preferences. You can see Atomic Blender or PDB is already checked. One last thing is just that all these boxes are checked. All right, now we're gonna import and prepare our residues. We're gonna go to File, Import, and locate our PDB file. Once the structure is in Blender, we're going to use Control-A and select Make Instances Real. The atoms are looking fuzzy like this because there have been duplicates made to make each its own individual object. So we're gonna go in and remove our duplicates. To delete them, we'll need to go in, because you can see when I select carbon ball 1 and carbon ball 2, they're superimposed. So it seems like we'll wanna delete every other carbon. So I'm just holding down the Command button on my Mac, and I'm selecting every other carbon and then clicking delete. Now we're left with clean, non-distorted carbon atoms that we can move around individually. So we're just gonna repeat this process. All right, the next thing that got in my way in animating is something called vertices. So what I do is I go through and select all the atoms that I wanna work with. Once I have them selected in the scene collection, I type in G and move them to a different location. And here you'll see all these little vertices dropped out. And so we're gonna delete those, being careful not to select our light. The last thing I do is in this scene collection, I delete the representative atom from each atom type. All right, so we're gonna be animating the whole molecule to move them into the right position and the individual atoms that are involved in the molecular reaction. To do this effectively, we're gonna need an animation handle by which to move around an axis. So if I move over to the 3D viewport on the left, I'll do Shift-A, and here I can select my empty object. So empty, plane axis. And you can see the empty handle here in scene collection. Now we're gonna link all the atoms to our handle. Let's select all of our atoms and type in G so that we can move the atoms to the center of our handle. You might have to change angle a little bit just to make sure that you've got it roughly centered. And from here, we're ready to link the two, the handle to all the atoms. All right, so now I'm gonna open up all these drop downs. And I'm gonna select our atoms, ensuring to select our handle last. And I'm gonna go back to the 3D viewport and select Control-P. From here, I'm going to select Object Keep Transform. And that should connect our handle to the 24 surrounding atoms of glucose. With that, we've prepared one of our monomers for reaction, but of course, we need 2 monomers. So let's right-click and duplicate. They duplicated right on top of one another, so we do need to move one from the other. So let's right-click and select, then type in G, and move one of your monomers away from the other. So now we have 2 glucose monomers with a handle. I prefer to name them differently so I can keep track of what's going on, so I'm just gonna rename these. There are 48 atoms in 2 monomers of glucose, 24 each, but only 4 are involved in the chemical reaction. To make the reaction easier to visualize, I recommend making these 4 atoms stand out a little bit. Let's start with our nucleophilic residue. So I went up here and I clicked select so it would highlight which one of the 2 monomers is the nucleophilic one. I'm going to reposition the camera a bit. All right. Each of our glucopyranose forms have a 1,5 ether linkage right around this oxygen atom. On the nucleophilic residue, it's the atoms attached to the 4th carbon that are involved in the chemical reaction. So these two. So we're just going to rename them to ensure that we can differentiate. I'm just going to add an asterisk to them. Now that'll make it easy to spot them under scene collection. So you can see the asterisk has been added there and here. But what about in the animation itself? To highlight the atom, we're going to select one and look at the bottom right panel, so down here to data and properties. So what we're going to do to make these stand out is create a different material property. When you select an atom, you'll see the base color changing at the bottom right. In this box over here, you'll see all of the properties of the material that's being animated. What we want to do is change the material link from data to object. We want to create a new material to place onto the object. To create the material, we're going to click New. Let's rename this. And since our oxygen has lost its base color, we can get it from another oxygen atom. So if we go over here to the HEX, we can get the code for the color that it was and change it accordingly. And I just changed the metallic value to 0.65 so that it has a little bit of a sheen to it to stand out in the animation. Now we're just going to repeat for the other atoms involved in the reaction. If you're concerned that the oxygen atom is going to stay this gray color, you can preview a little bit of what the shading will be by clicking over to this icon, Viewport Shading. And now you can see that we've successfully applied that metallic property onto those atoms. Now let's move over to the electrophilic residue. On the electrophilic residue, it is the C1, the carbon 1, and the oxygen attached to that carbon that are involved in the reaction. So we're going to highlight these two. All right, so now that we have the appropriate atoms highlighted, we can animate our reaction. To animate, we're going to break up the reaction into scenes like they do in the movies. Scene 1 is going to be the monomers side by side. Scene 2 is going to be orienting the monomers for optimal reaction. Scene 3 is going to be the bonds beginning to stretch. Scene 4 is the transition state. Scene 5 is the proton transfer and then the water formation. And then scene 6 is the glycosidic bond formation and the product separation. Let's just start with lights and camera. All right. So in front of our camera is where the animation is going to take place. So this little box situation is what the camera is. I've highlighted it. And if you want to toggle into camera view, you can select the camera icon. So you can see we're zoomed in really strongly on one of the residues. It looks like the nucleophilic residue. But we want to set this up in a way that we can see both the molecules come together and react. So that means we want to create our scene. Since scene 1 is going to be the 2 glucose monomers side by side, oriented roughly the same exact way, that way people who are observing the reaction can see that these are 2 monomers, we're probably going to want to zoom the camera out a bit. So if I get myself out of camera mode, and since I have the camera selected, I can use G to move the camera even further away. And now when we toggle into camera mode, the scene that we have view over is a little bit bigger. So at this point, what I think I want to do is go ahead and orient my 2 molecules so that they're side by side. I'm going to do that by selecting one molecule at a time. We've talked about how we can move its location with G, so I've typed in G and I'm moving it about. We can also rotate with R. If you type R a second time, it'll let you move in 360 degrees. So let's say we want to orient our molecule like this. And then maybe we can even lower it so that half the molecule is on one plane and half is on the other. So I'm going to try to situate it here in a quarter of the plane. And this will help when we're setting up our lighting. All right, so we have one molecule oriented. Let's select the second and do the same thing. Hopefully, it's quite obvious that these 2 monomers are in fact monomers. I've already set up scene 1, which is going to be showing these two molecules side by side. But let's check into our camera view. Our camera view would only be what is shown in the yellow box here. Let's zoom in a bit. If we're only showing what's inside of this yellow box, then the animation's only going to capture a portion of our molecules. It looks like we need to move our camera back a little bit further. Let's select our camera and use G to move it further back. Now let's check in. Better. You can also type in G while in camera mode, and you can move this way, which I think is kind of helpful. Let's move our camera back just a bit more. Really capture more of the scene. See how we're doing. Almost there. Perfect. We're doing it. All right. So now that we have our camera set up, let's think about where we want light sources to be. Of course, we can add more light sources if we want to, but I've only used one in my animations. And I'm just going to set it kind of in the center here. Of course, you got to change your angle and perspective a few times to make sure it's actually in the center. There's a life metaphor in there somewhere, but I can't think of one right now. And now I think we can move on to starting to animate the time sequence. The playback bar that's down here at the bottom, this is where the movement of the animation, where you can animate in Blender basically everything. So you could animate the camera moving, you can animate the light source moving, you could animate the metallic or the material properties that are affixed onto each individual object. It's kind of incredible and a little intimidating how much you can animate in Blender. So again, we're just going to take this step by step. In the timeline, you can see that there's a blue line and the number 1 here. That confirms that you're at the beginning of our timeline. This timeline is what we're going to use to keep track of what we want to show where. Let's start by selecting each of our molecules. Then we're going to right-click our selection here, and you can see options to insert keyframes. So we're going to insert a keyframe with a keying set. Key sets allow you to freeze particular parts of the animation at different times. So if you want it to only freeze on location and not its rotation or scale or any of these other properties, then you would just select that. For our purposes, we're going to do location, rotation, scale, and custom property. And you'll see in the timeline, a little yellow diamond is now there, which is confirming that we have set something to the timeline. All right, let's do the same for our other molecule. And just to be safe, let's do the same with our light and our camera. This is kind of like digital claymation. Instead of moving the objects and then freezing the frame, we're going to move the frame and change the objects. What that means is I'm going to change our frame here to 30. I don't know why, but it seems like animators work in increments of 30 when they're animating, so we're just going to roll with it. Now that the blue line and the number marker can confirm that we're on 30, we're ready to move on to the next scene. Keeping a little bit of distance between the two monomers, we're now going to orient them so that the atoms involved in the reaction are facing one another. This is another really good time to research how these molecules will be interacting in the medium that you're animating. In doing this process, I learned that the synthesis happens through a beta-phase nucleophilic attack, which means on the opposite side of the C6 alcohol group. All right, this part is crucial because once you have everything lined up and you know how you want it to look, it can be really easy to forget to set the keyframe. And then as you move through animating, nothing's going to change. It's just going to stay the same because it's only remembering what happened at the 1 marker. Now that we're at the 30 marker, let's go set our new keyframes so that the software knows that we want the molecules to morph from where they were at scene 1 to where they are at number 30. All right, so there's a few ways that you can check to make sure that your keyframe has been added. First, you want to see if there's a diamond. And to ensure that things are moving from scene to scene, you can see this kind of orange rectangle that's going on between the 2 yellow diamonds. The other way is to play the animation. So this part I find really exciting. Let's see how it looks. There we go. So they've oriented into where they will react. And now we're ready to start scene 3, where we're showing the bonds start to stretch. Let's think through what's going to happen. The C1OH bond is going to lengthen. Electron density is going to shift from this oxygen atom to this carbon 1 atom. We want to orient the camera in a way that it can perceive that. What I can do is copy that keyframe, move it to 30, and then select paste. What I'm hoping that does, let's see. If we start from start to finish, the molecule should move first, and then the camera should move. Great. Now the camera moved in a way that makes it really hard to see where the molecules are the entire time. So let's see if we can reposition it. I'm just going to very carefully move the camera through the molecules. To the opposite side. And where it's going to be really crucial is I'm going to try to rotate it as little as possible. Let's see how we're doing. Not bad. Right here, I think it will be perfect. So let's make sure we set our keyframe. And let's see how this looks. Got our camera view, got monomers, they reorient, and now the camera moves, and we have a really good sense of the fact that we're on the backside of the molecule. Now we can proceed. What's going to happen is that our oxygen of the C4 on the nucleophilic glucose is going to do the beta-nucleophilic attack on our electrophilic residue. As this is happening, we're going to see some bonds lengthen, enter a transition state, and then form the product. So our goal is to animate that. First step is to think about where we want our timeline to be. So since we have the camera moving to 60, I'm going to set it at 90. I want to move these two residues a little bit closer. So now that I have my keyframe set at 90, I'm going to select each one and move it in just a bit. All right, I'm really liking that. Insert keyframe. Explore what it looks like. It's looking like it's getting closer. That's good. Let's check the camera view. Loving it. So now I'm going to move to 120 and do the same thing. And I'm just going to move things piece by piece until they're right where I want them. One thing I forgot to mention that's really important is to save your Blender file periodically, because it can crash and then you lose everything. All right, now that we have our animation situated as we would like, we're going to set up the world background or the environment that these molecules are interacting within. To get a sense of what the environment around your molecules could look like, we're going to go to Shade. On the Shading tab, you can see this environment. You're going to go to the World Properties icon down here. Under Surface, you're going to click Use Node. You're going to go to the World Properties icon here and make sure Use Nodes is in blue. Then you're going to switch from Material Preview to the shader, which looks a lot like how it'll come out when you go to render the animation. To change the world or what's around your animation, you're going to move down here to this panel and select World. Now you're going to see the node setup that is configured for the world that you see in your 3D viewer window. we're going to add an environment texture. So we're going to type in Shift A and then go to Shader and Background. We're going to add an environment texture. To do that, we're going to type in Shift A, go to Texture, and then go to Environment Texture. We want to connect the color output of the background node to the color input of the environment texture. In the environment texture node, we're going to click the folder where it says Open. If you use your Finder, or if you have a Windows computer, some other way of searching for file names that end in .exr, you should find a repository of files that were installed with Blender, and if not, you can download them from the website. I'm going to use the Forest EXR for this example. There's a variety of ways that you can change the background by blurring it, changing the color. I'll let you experiment with that and keep things brief so that we can move on to rendering the animation. To render the animation, we're going to go to the Output Properties panel, which is right here. We want to ensure that our resolution is set where we want it. I use 24 frames per second. We're going to want to go back and check our timeline. Let's see if we can get to time. If we click on any of the objects that we've animated, we'll see the timeline fill in. What you want to do is make sure that your frame start and end are accurate for your given timeline. So I'm actually going to edit my end to 220. Then we're going to choose an out folder by clicking this folder. I use PNG for image sequences rendered through Eevee. We can see the render engine by clicking on this little camera icon. So now we're just going to ask the software to render. Here we'll just have to be patient and let the software go through and render the animation frame by frame. Once it's all been rendered, we can click out of this and switch the mode to Video Sequencer. To add your images into the Video Sequencer, type Shift A and move down to Image/Sequence. Here you're going to select all the PNGs for your animation. If we go back to the Output Properties tab, we can change the file format here to FFmpeg video. If we click on the encoding panel to expand it, under Container, we're going to want to select MPEG4. For our output quality, we can change it to high. And again, we're going to go to Render Animation. Blender's going to process that sequence as it's showing you and save it to the folder that you selected. All right, let's test our animation. Bye, water. There it goes. And that is how you use Blender as a chemist to create 3D molecular animations. It's not perfect. This is only after I've done one animation in my career. So be gentle and feel free to suggest ways I can improve. Next week, we're gonna explore the material science of the soccer ball. But in the meantime, check out our last episode of the Curious Scientist podcast, where we explore the 5 qualities of exceptional STEM mentors. Bye.